Now I'm recording. Right, so let's see. When is the exam? December 7th? That's a Monday. Is that a Monday? Let's see. It's a Tuesday. It's my mother's birthday. Uh, and I'm leaving on the Sunday to go to. Why am I leaving on the Sunday? I could have gone on the. No, I'm leaving on the Sunday to go to London, so I'll be dead the day. So we'll do a review session on the 4th or the 3rd, and then it's due on the 6th. It's due before the exam. It's going to be due midnight, Monday, the 6th of December. So yeah, that's what we're going to do. So shall we move the thing till tomorrow? Why do I have an orange bar around everything here? Let's try something again. Well, apparently you do have a bar around it. Anyways, so that's what it is. Now I lost everything again. Chat. So that means we should write an email to Ben. Phase 5 extension. Hey Ben, can we make phase 5 to Wednesday rather than today, i.e. tomorrow? So phase 6 is due Monday, December 6th at 11:59 p.m. That is true. Right. So now we're at code generation. We've talked about. So, oh, by the way, sorry about sorry about the issues over the update of the reference compiler, but there was something that was horribly bad, and we fixed it, and then that broke something, and it should be all right now. And then there's a test that fails in phase 3. You can delete that one or keep it. It doesn't matter. Right. So anything else on phase 5 before I talk about code generation? Yeah. Oh, there you are. It's about bloody time. Do you grab a new espresso? You know, because the reference is online, so you never you never have to update anything in order to use a new reference, the new reference compiler. You should be fine. Right. So no questions. Let's do something then. So can we just? Oh, I just want to check something. This should be fine. Wait a minute. There. So 1, 2, 3, 4, 5 more lectures. Yeah, that's okay. So let's do something. Are you allowed to use type.parse signature? Sure. What do you want to do that for? How do we check if a method is being re-implemented? Oh, now all the questions are coming out. Well, how do you check if it's being re-implemented? You should be able to call find method on the superclasses all methods and find the exact same method somewhere above. Did that answer that? I think it did. So let's start by talking about intermediate code, of course. So we, at the very beginning of the course, talked about intermediate code in some way or form, and said, well, it could be it could just be the parse tree carrying through to the final code generation phase, because it is possible to do optimizations and rewritings of the parse tree as well. But we could also generate some fairly abstract machine code-like code. So, for example, let's look at 3-address code, which is very much like a machine code-like thing. And also, let's look at a stack machine language, which might be, in some ways, more suited to Java. So let's start with a 3-address code. So that's 811. So in general, all instructions look something like some left-hand side is equal to some right-hand side that consists of an operation applied to two operands. Right, so then we could ask the question, what do we need? Well, we probably need assignments. So it could be something like x gets the value y. It could be x gets the value y of z, or maybe it makes sense to have the unary one as well. Okay. Now, we probably also want some conditional jumps. So, for example, if x op y go to L, or maybe if z go to L. Oh, you know what? Should I move this onto the... I'm going to move this onto the next page so we can get them all at the same time. So I'll put them there. We might want an unconditional jump, so that's easy enough. That's just a go-to, isn't it? Now, of course, we don't really need it. That's equivalent to if true go to L, but it's just a little nicer to have, isn't it? Now, is there anything else we need? I don't think there is anything else we really need, because we have state, we have conditions, and we have operators. So that's about what we need, right? But we might, it might be nice with some more stuff. So, for example, procedures, calls, and returns. So, for example, call p comma n, and that will call procedure P with n parameters. So this is procedure name, and that's the number of parameters. We could have a param x that just specifies that x is a parameter, and then we can have return y. It might be nice to be able to do address stuff, i.e. pointers. So we could imagine that we could say things like $x and $x to get the address of something and to dereference that again. So we could just do a couple of examples here. So for example, T1 is the value of $y. T2 is I times 4. T3 is T1 plus T2. And x is equal to star T3, right? So that just gives you the next element in an array of some sort, right? So this is basically x equals y of I. So let's try another one. So how about something something something? X is equal to 6 times y minus b divided by c. If x is greater than 100, then call f of x comma y plus 10, and then do y equals minus 9. So we could translate that in the following way. T1 gets to be 6 times y. Remember, it's 3 address code, so we can only do 2 operands on the right-hand side. Then we can say T2 is b divided by c, and then we can say x is T1 minus T2. Then we can say if x is greater than oops, here's a mistake. There's a mistake in the book. It should say if x is less than or equal, not greater than or equal. I'll put L1 down here, where we will say y gets the value of minus 9. And if this is the case, then we'll say T3 gets the value of y plus 100. And we're going to make x a parameter and T3 and call f with 2 parameters. So we could do something like that. Now that might work fine for a regular procedural language, and if we want to do an object-oriented language, then we might have to extend this to work with objects as well, and that's sort of what the next part talks about. I'm not going to bother with that. You can just read those 2 pages yourself. But I do want to just talk a little bit about parse trees to postfix. Because we're going to need that. We're going to need that later. So let's take a look at a minus b minus c times d divided by e. Now, what does the parse tree look like for that? I think it looks something like this. Is that right? What does it look like in postfix? So in general, A plus B is equivalent to AB plus, right? So if I said, okay, I'm going to take this part here and I'm going to call it X, and if I take this part here and I'm going to call it Y, and then let's say that P is a function that takes infix trees to postfix, or infix expressions. Then P applied to A minus B minus C times D over E is going to be, well, it's going to be P of X, P of Y minus. You've all seen this before, right? This is not there's nothing novel in this. So the rule is simply recursively keep doing left, right, and then operator. So now, of course, this P of X guy is just going to be P of A, P of B minus. But P of A is just A, P of B is just B, and minus is just minus. So we get that. So all in all, we get that A, B minus CD star E divide minus. Now, why is it that sometimes we like to turn things into postfix notation? Does anybody remember? I didn't even get a Pepsi today. Things are just going bad. Oh, normally I have coffee here. I just get Pepsi for the next one. That's right. I'm getting old as well. It works well with a stack. Yes. So if I want to evaluate, if I don't have any registers and I want to evaluate this on a stack, then this works really well, because if I take this and I translate it in the following way. Push A, push B, subtract, push C, push D, multiply, push E, divide, subtract. Then if we just sort of try to play it, then push A will have A on the stack. Push A, B will have A, B. Subtract, I will take A and B off and then add A minus B. Push C, we have A minus B. So that's one element, one element, one element, one element, one element, one element C. A, B, C, D. Multiply, well, A minus B is still on there. D times D is now on there. A minus B, C times D. That's a value, that's a value. E, that's a value. A minus B is a value. Divide takes two things off and then divides, we get that. And subtract takes two things off and does the division or subtraction. So we end up with just that one value there, right? And actually, in and JVM bytecode, if the address of A is 1, if the address of B is 2, C is 3, D is 4, and E is 5, and all are integers, then we would get something where we just say I load, so integer load address, the value at address 1. Integer load the value at address 2. Integer subtract I load address 3. I load address 4. Integer multiply I load integer load value at address 5. I div I sub. So that's what we get, and we can see that if I look at the tree, so I have the x part and the y part. So this is the x part from the previous page, and that's the y part. So you can see how to generate code for this, if I have this in a tree, is to go and deal with that. That'll leave the value of that on top of the stack. Now go and deal with this. That'll leave the value of that on top of the stack. Now issue that operation to do that, right? So if I look at what this does, those two things after that sub will look like that. Then I start and do this, and when this is done down here, we end up in this situation when I can now do that. So the JVM works with a stack. It doesn't have any registers, and therefore we translate all our arithmetic into postfix notation. And it really is as simple as this. So it's deal with the left start, deal with the right side, issue the right operation to do. Right. We'll come back to that. Let's take a look at abstract stack machines. This might remind you a little bit more of some of those horrendous things that Ben probably did in 326 when he talked about semantics, right? So let's define an abstract machine, and I'm going to call it M, and it is going to be a quadruple, I guess, of M sub I, M sub D, S, and PC. This is my program counter. Take a while, guess what S is. That's the stack. And this is the program. What do you think that is then? What do we need? What am I missing here in order for this to be some sort of reasonable machine? Input. Who needs input? States. Yes. States. So where are states located in programs? Locals and parameters. Where do locals and parameters live? A little bit more specific than just memory. We don't have any registers. And it's, well, so in general we do have registers maybe, but you shouldn't say that locals and parameters live in registers, because what if there aren't enough registers? So they by definition live in the activation record. The activation record is not on the heap, but on the stack. Not on this stack. This is an operand stack. So this is to do arithmetic. This D here is my activation record. Okay. So that's the stack of what we normally know. So we know that the current instruction is a program at PC. That makes sense. Right. So what do we have? We have a whole bunch of different instructions that we can do. I have push V, which pushes the value V on top of the stack. So okay. Now, what do I have to do if I say, right, my machine consists of these things here? And what happens? So what happens when you execute a program? I mean, what happens inside the computer? You have state change, right? So in order to execute a program, you have to make the appropriate state change. All right. So if I ask you, if I push a value onto the stack, what happens to these four things that make up my machine? Is there any change to the program? No. Is there any change to the activation record? No. Is there any change to the stack? Well, yes. The stack now has another value on top of it. And is there any change to PC? No. So what we can do over here is we can simply say we're going to list what the changes are to the things that have changes on them. So if S, which is the stack before we did this, is v1 dot 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 vn, then the stack afterwards is v1 dot 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 vn and v. So we push that time there. Then what if I want to push the value of something? So of a variable, for example. Here we'll call that R value E. So it pushes the value. I'm just going to move that up a little bit. Pushes the value. Oops. Of the variable E onto the stack. Now, we have all the state located in MD, and its location is, we'll say, %E. So we can now say that S before was V1 dot 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 Vn, and S afterwards V1 dot 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 Vn. MD at %E. So we get that. Right. We can also do L value of E, and that pushes the location of E, which is %E, onto the stack. So nothing particularly complicated here. we get something like that. Right, pop. So we can pop the stack. Oops. So if S is V1 dot 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 Vn, then S prime is V1 dot 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 Vn minus 1. There we go. We can also do an operation, and let's assume it's K array. One R. So it takes K operands. So it removes K operands from the stack and pushes the value, whatever you get from applying the operator to those K things. So if the stack again was V1 dot 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 Vn, actually, let's do another one first. Let's say that R is the operator applied to Vn minus K plus 1 dot 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 up to Vn. S is therefore V1 dot 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 Vn minus K, Vn minus K plus 1 dot 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 Vn, and afterwards those top elements are gone and replaced by the value of R. Right, what else? Copy. So copy is the top element of the stack if S is equal to V1 dot 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 Vn. Then S prime is just V1 dot 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 Vn Vn. Oops. We can do an assignment. So this removes an R value, E, from the top of the stack, as well as an L value, which is immediately below, and stores E into, what should we call that L value? Should we call it V into MD of V? Right, so again, S is equal to V1 dot 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 Vn minus 1 Vn. MD prime is equal to, actually, MD prime of Vn minus 1 is now equal to Vn, and S prime is V1 dot 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 Vn minus 2. All right, a few more. So that defines a label. That doesn't really do anything. It just becomes a place we can go to. And this is that's unconditional jump. Well, what does that do? Well, it changes something. It changes the program counter to be the address of L. Then we can say something like go false L, which is jumps to label L if the top element is true. So if S is equal to V1 dot 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 Vn, then PC will be equal to ampersand L if Vn is false and S prime is V1 dot 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 Vn minus 1. And then we could have go true L, which is very similar to that. And we could add support for calls of procedures. Which is sort of interesting because if we think about that, actually, let's just talk about that for a second. So if I have call fm, so what is going to happen if I do that? Well, we're going to have to create a new machine, m prime, where m prime of I is the code for f, md prime an activation record for f with m parameters plus the locals of f, and m prime d of I is then vn minus m plus I plus 1, and the new program counter is starting at 0, and finally S is equal to the empty stack. So what we do in this case, we have to create a brand new machine because we need to execute a different kind of code, and we need a new stack that's empty, and we need a new activation record. So the easiest thing to do is simply create a new machine. Right. So those are some options that we have, and of course, if we translate our code to either stack machine language like we have here or 3-address code, then there's got to be another translation someplace that will do a further translation of that into the right thing. So both of the ones we looked at here sort of didn't emphasize registers. So let's talk a little bit about registers. Even though the Java virtual machine does not have any registers, I think it's important that we talk about it anyways. So let's go to 8.2, which is register allocation, and this is a fascinating topic. Although we don't need it in the assignment, I want to talk about it because I just thought this was just this is really, 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 really cool. And it's one of those things where you use almost everything that you've learned in your degree to do this. But in order for us to do this, we have to talk about life and death first. So we'll need to start with 821, which is live and dead variables. It's not relatives. So let's start with a definition. It's a good place to start if you're stuck. So it goes something along the lines where we say a variable x is said to be semantically live. That's why I'm using green. At the instruction I, if there exists some execution starting at I whose state or behavior can be affected by changing x. So basically, you can think of a variable as being live if it can in any way live at some place, because we're always talking at a location in the code. If a change in that variable can have any effect on the code in the future. So if for example I said something like x equals 7 and then I say y equals z plus 3, w equals y minus 4, then I can ask, is x live? Well, it doesn't matter what I do to x, it's not going to change. It's not going to change anything at all. So x is not semantically live at where that arrow points to. Now, the same variable is syntactically live if there exists I should say live at the instruction I, if there exists a path to the exit in the control flow graph, which we haven't talked about yet, where x may be used without being defined. A variable that is not live is dead. There we go. Right. So we'll come back to control flow graphs in a little while, but basically the idea of a control flow graph is to divide the code into a graph-like structure that shows how well control flows. Therefore, the name control flow graph. Now, let's take a look at an example here, so we can sort of gain an idea of what the difference is between semantically and syntactically liveness. So I'm going to put some line numbers: 1, 2, 3, 4, 5, and 6, and then we'll put some code. Int x equals y times z if y plus 1 times y plus 2 is equal to z, then x is equal to 1 if y times y plus 2 times y plus 1 is not equal to z, then x is equal to 2. Return x. Right, so now consider x in line 1, so this guy. Is it live in line 1? There are two options. Semantically and syntactically. Anybody want to take a stab at that? So Benjamin says it is not syntactically live because it always gets redefined. Oh, but that means it's not semantically alive, right? That's what that means. Because what and how do I know that? How do you know that, by the way? No, Daniel, you oh yes, sorry. No, the other yes, sorry. Yeah. Yeah. I think I need to go home and sleep. Daniel says syntactically alive, semantically dead. Should have used a comma to make more clear. No, that's fine. So Benjamin said, so Benjamin's answer wasn't correct, but he is correct in saying that it gets reassigned. How do you know that it gets reassigned? I suppose Daniel also noticed that. How do you know that? From a semantic point of view, how do you know that x gets reassigned? Yeah, one of so Benjamin says because either the equal equals z or the not equal z is true, right? One of them will be true because what did I do here? Well, that expression is the same as that expression. So if this is true up here, this is false down. This is false down here. If this is false, this is true because that is just a negation of that operator. So if I don't end here, I will end here, and if I don't end here, I would have ended there, right? So we can say since y plus 1 squared is y squared 2y plus 1, and equal equal is the opposite of not equal, we always end in line 3 or 5. Therefore, x in 1 is semantically dead. Why is it syntactically alive then? I suppose we can say dead, alive. Now I feel like saying "You spin me right around like a record baby," but that was a Dead or Alive song from the '80s. But none of you remember that because your parents weren't born, or something like that. Oh, then you're Benjamin. Then you're old, or you're listening to KKLZ. Um, oh, I guess you're all old then. Uh, I promise you, Um, I will not attempt to sing it because I don't dislike you all that much. Um, so why is it alive from a syntactic point of view? I mean, we could try to take this thing here, couldn't we, and do the following. I'm just going to try something here and say, right, um, int x equals y times z. I'm going to put that in a little box by itself. And then I'm going to say, what happens next? Well, what happens next is that I'm going to do y plus y times y plus 1, sorry, y plus 1 times y plus 1 equals z. And I really have sort of two outcomes here, right? I can have an outcome that says true, and I can have an outcome that says false. And if it is true, then I will do x equals 1. And then what? Then if it's false, then I will look at y times y plus 2 times y plus 1 not equal to z. And I'll actually do that in the false case as well. I just didn't do the assignment. All right, that has the same option. It can be, I'm running out a little bit out of space now here, so we'll bend this around. If it's true, then x gets the value 2. And after that, I do that. Now, the important things about these little boxes that I drew here was that they contain pieces of code that always gets executed together. So basically, if I start at the very beginning of a box, then I end up doing all the code that's in that box, right? Now, if I look at this, then, you know, how many, so let me ask you semantically here. How many different executions? Oh, so let's just see what Benjamin says here. He says, so even though they'll never both return false, we consider that a valid path in the control flow graph. Yes, because we're looking at it from a syntactical point of view. That's exactly the point, right? So if I asked you, just let's answer this question first, and then I'll come right back to this. How many different executions semantically? So if you look at this code and you're looking at it and you're going to execute it, how many different executions can I get? And we can do it by just listing the line numbers that get executed. Well, we know that we either end up in 3 or 5, line 3 or line 5. So it's going to be something like 1, 2, 3, 4, 6. 1, 2, 3, 4, 6, or 1, 2, 4, 5, 6, right? And I think the point here is sort of the fact that it's either 3 or 5. 1, 2, 4, 6 are always there, right? Now, if I look at that from this point of view, actually, let me just put the line numbers on here. So this is line 1, line 2, line 3, line 4, line 5, and line 6. If I just look at this as a graph, then I can go, well, actually, so we can ask that question. How many paths from 1 to 6 in there exist? Well, let's see. 1, 2, 3, 4, 5, 6 is 1. 1, 2, 3, 4, 5, 6. I can go 1, 2, 3, 4, 6. 1, 2, 3, 4, 6. I can go 1, 2, 4, 5, 6. 1, 2, 4, 5, 6. And I can go 1, 2, 4, 6. 1, 2, 4, 6. Okay. Now, if we look at that, we can see that there's a 3 there, there's a 5 there, there's a 3 and a 5. So we have the option of doing one of these two, which are the ones that can actually happen, but just from a syntactic point of view, where I don't actually know that these are opposite of each other, I could take the one where I do both of them, the one where I do neither of them, the one where I do the first one, which is, the one where I do the first one, which is possible, or the one where I do the second one, which is possible. So that's this one and this one. That's the same as those guys over there, right? But from a syntactic point of view, both if statements could be true, or neither if statement can be true. So I get more options in terms of the graph. Now, which one do you think we should be doing? Okay, so struggling to understand the semantically live or dead part. Can you explain how we can see this is semantically dead one more time? Right. So the definition of semantically live is that at some instruction, if there exists some execution starting at I, whose state of behavior can be affected by changing X. Okay, if I change this to 77, is that value there ever going to change? No, because if I go there, if this is true, that'll happen. If this is false, then this will be true, and this will ever happen. So I can make whatever changes here. The point is that between here, where I assign X, and here, where I use X, there's always another reassignment to X. So this X value here is never the one that falls through to there, right? If this X value could fall through to here and be the one that is executed here and returned, then X would be alive here because any change here would change, right? So is X alive on lines 3 and 5? Yes, it is. Because a change here, if this is true, would change the value that gets done there, right? Actually, it's alive right there. It's right alive right after, but not before. So what do we think? Should we attempt to do semantically live or syntactically live? What's better? Well, it's obvious that we should not attempt to do semantically because that's better and impossible. Because why can't I do semantically liveness? Anybody? So now we're sort of in the realm of 477, I think. What's the problem with trying to calculate semantic liveness? Well, you kind of need to know what the values of everything are. And if you know what the values of everything are, then you could. Aren't we just talking halting problem all over again here? This just seems like this is never going to work, right? So we kind of have to run it in order to see what happens. So semantic liveness is out. Syntactic liveness, long live. Now the problem with syntactic liveness is that it is not always correct, but it's the best. It's the best we can do because that we can actually compute, and it's fairly easy. So let's take a look at that, and let me just give an extended definition of when something becomes live or dead. So we can say that not in that color we can. An instruction I makes a variable live when it references it or uses it. So basically, if it appears on a right-hand side somewhere in an instruction, then the variable comes to life. I think I lied when I just said yes to the fact that it's semantically live there. It's not. It's semantically dead there as well, I'm pretty sure. An instruction I makes a variable, should we call it red? Dead. When it defines it. No, actually, I want to retract that. It's live here and here, but not up there. Okay. So, see if I can draw a nice little line here. So if I have my program flow down, then I'm going to draw the arrows in the opposite direction, and then I'm going to have an instruction here. We'll call it I. And then I'm going to define a set here, and I'm going to define a set here. So I'll have a set immediately before the instruction, and I'm going to call this the live in of I. So that's the set of variables that are live before I. And these are the ones that are alive after I. Okay, easy enough. Then we just need to define something else real quick here. So I'm going to define something called a def set of I and a use set of I. And the def set is all the variables in I that are assigned to. And the use set is all the variables in I that are evaluated. Or referenced or used, depending on how you want it. Right. So what we can do now is we can say, all right, what are my options for this instruction that I have here? Well, it could define a variable, it could use a variable, or it could do both. So for example, x equals x plus 1 is an example of something that does both. So let me just do those real quick, and then we'll call it a day. So if I have a use of x, a def of x, a use and a def of x. Then, since I'm using x here, it would be alive before, and I don't know what's down here. Something. If I have a definition, then if it were alive before, then it sure isn't anymore. And if I use it and define it, it won't change anything. So if I use of x, it makes it live above. If I define it, it makes it dead above. So nobody really says that that x necessarily is in there, but it's definitely not in there. And in this case, that makes f alive above. So let me finish almost on time with a way to compute this set based on this set. So would you agree with me if I said that the live in of I is, well, it depends on the live out set, but anything that I define, I seem to kill off. All right, so we'll take that out. So we'll take out of that the def set of I. But all the stuff that I use comes to life, so we'll union onto that, the live set of, or the use set of I. So now I have a relationship between the live set before an instruction and the live set after. And I should just quickly notate these. So we're doing them in the opposite direction of control flow, because the one above is based on the one below. So we start at the bottom of the program and then we calculate these sets all the way to the top. And here's the thing, right? If the live in set of the very first instruction contains anything, what does that mean? Well, let's just go back here real quick. Same variable is syntactically live at I if there exists a path to the exit in the control flow graph where x may be used without being redefined. So if a variable is syntactically live at the very beginning, then there exists a path where it may be used without being reassigned. Well, that means that there's possibly a use of a variable that doesn't have a value. I.e., we can say if there's a live inset of the very first instruction of a procedure or program that has some variables, and those variables could potentially be used without ever getting a value, and we can say, hey, these are not initialized. That's phase 7 of the Espresso compiler that does live variable analysis, basic blocks and control flow graphs, and all that fun stuff. And that one you can get to do from December 12th to December 24th. All right, that's it for today, unless there are any questions. No, that's it. All right, then we're out of here. See you guys on Thursday or tomorrow or whatever.